Okay, we're at the end of chapter 5. In this video, we're going to go through the final section of chapter 5, which is on the half angle identities. So if we take a look at the trig identities sheet, up to this point, we've covered everything here. So the fundamental identities, the sum and difference formulas, the cofunction formulas, the double angle identities, the product to sum and sum to product, and they're also in some trig identity sheets, they'll include things like the conversion factors for going from degrees to radians, and here's just the periodic formulas. So yeah, if you take sine of theta plus the period times any integer, positive or negative integer, you just get sine back. So we're not going to go through these, but some trig identity sheet don't include those. But so just the main trig identities that we derive in trigonometry, we've covered all of them, and all that's left is the half angle identities. All right. From alternative forms of the identity for cosine 2a, we derive identities for sine of a divided by 2, cosine of a divided by 2, and tangent of a divided by 2, known as half angle identities. Okay, so the double angle identities, it was like the sine of 2 times an angle, cosine of 2 times an angle. Half angle identities, we're dealing with sine of not 2 times an angle, but 1/2 times an angle, cosine of 1/2 times an angle. We derive the identity for sine of a divided by 2 as follows. So they said, we're going to start with a double angle formula. So cosine of 2x we know is 1 minus sine squared, 1 minus 2 times sine squared of x. That's from a double angle identity. They solve for sine x and get this. And it just notes, remember to include the plus and minus. Now, if you starting from here, if you let 2x equal a, which means that x is equal to a divided by 2, then you could substitute, x for a, 2, or x for a divided by 2, 2x for a, and there is the half angle identity for sine. The plus and minus symbol indicates that the appropriate sign is chosen depending on the quadrant of a divided by 2. For example, if a divided by 2 is a quadrant 3 angle, we choose the negative sign because the sine function is negative in quadrant 3. All right? We derive the identity for cosine of a divided by 2 using another double angle identity. So cosine 2x, they use not 1 minus 2 sine squared of x, but 2 cosine squared of x minus 1. Solve for cosine x, make the substitution to where you get cosine of a divided by 2, and there is the half angle identity for cosine. Now, an identity for tangent a divided by 2 comes from, that's one way you could do it. There's probably different ways. I'm sure you could get to the tangent of a divided by 2, but you could do, that from the quotient identity, that tangent a divided by 2 is equal to sine of a divided by 2 divided by cosine of a divided by 2. And that's what they plug in here, simplify, and get plus or minus the square root of 1 minus cosine a over 1 plus cosine a. So there is the half angle identity for tangent. Okay, now they derive an alternate identity for tangent a divided by 2 using the double angle identity. So yeah, you could still, you could use the double angle identities not to get to the same half angle formula, but an alternate one. So they do, let's see, tangent a divided by 2 is equal to, so they still use the quotient property, but then they say, so 2 sine a divided by 2 times cosine a divided by 2. Okay, they multiply the numerator and denominator by 2 cosine of a divided by 2. So this, they can use the kind of they use the double angle formula. You can use the double angle formula with, it seems like maybe you couldn't because it's a divided by 2, but it's, if you think of the angle as 2 times a divided by 2, right, then you can convert this to, you can apply the double angle formula on anything, and they apply it here and convert this to sine of 2 times a divided by 2. And then here they use the double angle formula for, that was for sine, the double angle formula for sine, and then in the denominator they use the double angle formula for cosine to convert this to 1 plus cosine of 2 times a divided by 2. And then which is, so 2 times a divided by 2 is just a, and so there you go. There's another form of a half angle identity for tangent. And then they actually do another form for the half angle identity for tangent. From this, you could just, we'll do this. I'll derive this in the separate dedicated derivation video, but they derive a third one here for the half angle of tangent. So there's the half angle identities for, you have cosine, sine, and then 3 forms for tangent. Okay, now, similar to other identities, if you wanted, let's say, secant of a divided by 2, so that would be, let's see, the reciprocal of secant is cosine, then it's just the reciprocal of this, right? And, you don't have to just write it as 1 over plus or minus. You could simplify this. I want to say you could just take the reciprocal of what's inside the root. I'd have to look at it, but, play with it and simplify it. But that's it. Reciprocal of sine of a divided by 2, reciprocal of this is cosecant a divided by 2, etc. Because that's what you might be thinking, can you do that? Yeah, you can. It's the cosine, so of any angle. Well, let me do it this way. Let's say cosecant of any angle, no matter what it is. So I'm going to put a divided by 2, but I could say that u is equal to a divided by 2, and I've got cosecant of u, right? I can write that as 1 over sine of u. I can write this as 1 over sine of a divided by 2. That's completely valid. Whatever the argument is in the trig function doesn't matter when it comes to the trig identities. You just have to use that same argument all the way through the identity. Okay, now, if you notice, though, if you look at so 3 of these identities have a plus or minus, but 2 of these actually don't, which is interesting. So, why is that? 3 of these identities require a sign choice. When using these identities, select the plus or minus sign according to the quadrant in which of the angle. For example, if the angle is, we know how to do this. We've learned how to work with a plus or minus when it comes to a trig function, right? It's still a function. It doesn't mean that this it doesn't mean it's not the idea of there's multiple outputs for the same input. It's not like that. We're still dealing with trig functions. And we know how to do this. Like if the angle is 324 degrees, then a divided by 2 is 162, which lies in quadrant 2. So that means that, if we had cosine of an angle in quadrant 2, tangent of an angle in quadrant 2, we know the signs of those. So we can choose we can keep the plus or the minus, depending on the circumstance. Now, how do these not have a plus or a minus? Because it works out to where it's the main idea is there's like a mixture of 2 separate trig functions in here, and it works out to where the sine and the cosine are going to end up giving you the correct sign in the end. You don't have to choose, right? The sine's going to be positive or negative. The cosine's going to be positive or negative, so it's going to work out where you don't have to choose. Whereas, I'm not saying that's the hard rule. If there's a mixture of trig functions, there's never going to be a plus or minus like that. And you can think of it just to give you an intuition, like these only have a cosine, one trig function. So they don't have another trig function to interact with to automatically cancel out the sign and give you the correct sign. But I'm saying but you still might have a case where you've got a mixture of trig functions and you still need to have a plus or a minus just because of the way it works out. Okay, now you might have noticed this, but if we come back to the trig identities sheet, here are the half angle formulas, and that's different than what the textbook just gave us. What is this? Well, this is just those same half angle formulas in a different form, written in a different form. So if we come back, and some trig identity sheets will give you these, some will give you what you just saw on that trig identity sheet. So, okay, if we come here, let's say we're at this step. Okay, from this step, let's instead of doing what the textbook did, let's square both sides. So, all right, what happens is we get sine squared of x is equal to, and now there's no more plus or minus, and we just get rid of the radical because we're squaring both sides. 1 minus cosine 2x over 2. Okay, now we can just rewrite this on the right side as 1/2 1 minus cosine 2x. Okay, and there you go. That's what is sometimes you'll see referred to as one of the half angle identities. If we come back here, so sine squared of theta is equal to 1/2 times 1 minus cosine 2 theta. Now, and there you go. So now I personally like, to me, when I think half angle, I'm thinking it's a half angle, like a double angle. You know, you look at this and you think, what does half angle mean? So, but, you know, I mean, it depends on the circumstance. Maybe this is more useful. Maybe these are more useful. But you could derive, if we come here, you would square both sides here and get cosine squared x is equal to 1/2 times 1 plus cosine 2x. And, okay, yeah, if we come back, there's cosine squared x is equal to 1/2 times 1 plus cosine 2x. And then, yeah, this, we just square both sides, and we square both sides of this here. And you get tangent squared of, well, no, it would be, so you would do, let's take, so here we have cosine x here. Let's divide the sine x at this step by the cosine x at this step. So that's sine x divided by cosine x. It is tangent x. So, okay. So that was plus or minus 1 minus cosine 2x over 2. And then 1 plus cosine 2x over 2. And let's see, they simplify this. They just combine what's in the roots. So let's see, if you divided these two, you would get 1 minus cosine 2x over 1 plus cosine 2x. Then you square both sides. So tangent squared x is equal to 1 minus cosine 2x over 1 plus cosine 2x. There you go. Okay, now here's some example problems using a half angle identity to find an exact value. So found the exact value of cosine 15 using the half angle identity for cosine. So yeah, this opens up the door for finding exact values of angles, and I'm wondering if this allows us to venture out from just angles that are multiples of 15 degrees. So I mean, I guess you could use any trig identity to find an exact value of a trig function of an angle. And so I'm wondering, with what kind of, if you take all of the trig identities together, what angles can we find exact values of trig functions for? So, because we could use the double angle identities as well, right? I don't think we talked about that, finding exact values of angles with the double angle identities, but we could. So let's see, could we get with a double angle identity, is there any angle we could double and then get some angle that is a multiple of something other than 15? So we would have to start with an angle that's a multiple of 15 and then double that and then get some angle that's not a multiple of 15. Can we do that? I don't think so. So like 105, that's a multiple of 15. If you double that, you get 210. So is 210 a multiple of 15? Yes, it is. Okay. And so with that, I don't think the half angle identity, it's the same idea. We have to start with an angle that's a multiple of 15, And then if you half it, you get an angle that's not a multiple of 15. Then we can expand out to get exact trig function values of more angles outside of just the special angles, quadrantal angles, and angles that are multiples of 15. But all right, so yeah, they're going to write cosine 15 as cosine of 30 divided by 2. And so then you use the formula, and you just have to evaluate cosine of 30, which we can do. It's a special angle. So you get cosine 15. But we also got cosine of 15 with the sum identity for cosine. Okay, find the exact value of 22.5. Well, 22.5 times 2 is 45. So you can use the half angle identity. Well, there you go. There's an angle that's different. 22.5, that's not like a factor of 15. So you can find an exact value for 22.5. And so you can take take 45 divided by 2, take 105 divided by 2. So 52.5, you can find an exact value for 52.5. So there you go. So actually, this does open the door for more exact values of angles. So there it is. Root 2, the tangent of 22.5 degrees is root 2 minus 1. Okay, now here's more problems like, so if we know that cosine of s is 2/3 and s is between 2 pi and 3 pi over 2, so the fourth quadrant, find sine of s, the half angles for sine, cosine, and tangent. So we could use the Pythagorean identity or whatever to get sine of s, and then we could also get tangent of s, just divide sine by cosine. And we know that we can do that because we know the quadrant of s, so we know the sine. So they get, let's see. Then, so if we have sine, cosine, and tangent of s, then we can get any of these half angles of cosine of a divided by 2, sine of, or s divided by 2, sine of s divided by 2, etc., because we have cosine of s, we have sine of s. And that's what they do. And we'll work a bunch of example problems. Simplifying expressions using half angle identities. So here for both of these, they see how the pattern matches up with the half angle identity formulas and simplify from there. We'll work a bunch of examples like this and then verify the following identity. We're going to do verifications of equations as identities. We'll make use of the half angle identities as well. We'll do all this in the next video.